Hello, and welcome to the lecture for Chapter 10 from OpenStax Astronomy. We're going to continue our discussion of the planets of the solar system, talking about Venus and Mars. In Chapter 9, we talked about Mercury and the Moon, which yes, the Moon is not a planet of the solar system, but we made a lot of comparisons between Mercury and the Moon. But now we're moving on from these very desolate worlds to perhaps less desolate worlds, because we're saying they're Earth-like. What do we mean by that? Well, let's find out. So we're going to be talking about Mars. First, we're going to get into Venus, but it's great to start with this photo of Mars because it shows the scientific and engineering accomplishments that we've made in terms of studying the red planet, because Mars is known as the red planet. We have sent not just landers and orbiters in terms of space probes to Mars, we've also sent these rovers that will drive themselves around with some autonomy, some control back from Earth, but make all kinds of interesting discoveries on the surface of Mars. And we'll talk more about those later. Now, an interesting summary about Earth, Venus, and Mars can be laid out in this table from your textbook. One thing that we can see right away is the actual size of the orbits. So Earth is exactly 1 AU, because that's how 1 AU is defined in terms of the average distance of Earth from the sun. Venus is a little bit closer to the sun, not half the distance, just a little bit closer. And Mars is 1.5 times further. They're all essentially in the so-called habitable zone, more or less, of the solar system. Mars is definitely further out, so it's a colder planet. Venus is closer in. But it turns out there's a lot more to these planets than just their location around the sun, because Mars is much colder than we would expect, directly comparing it to Earth, and Venus is, as you'll soon learn, much, much hotter than we would expect based off this row alone. Now, if we take a look at the actual year, we can find out that the year of Earth is 1, of course, because that's how it's set. Venus has a somewhat shorter year, and the Martian year is almost twice as long. In terms of mass, Venus is almost the exact same size, which I'll jump down to the next column here. We can see in terms of the diameter, Venus and Earth are downright almost identical, but Venus is significantly less dense. It certainly has a less dense core, and that means that its overall mass is only 82%, despite it being almost the same volume. On the other hand, the mass of Mars is only 1/10 the mass of Earth. And that's because if we take a look at the radius, or rather the diameter, we see the diameter of Mars is only half the diameter of Earth. So we can think of Mars as being half the size across, which of course, if you're half the size across and then you square a half, or you cube a half, so you take a half to the cube power, well, that's proportional to volume. So if you're half the size in a linear measurement, then you are 1/8 the volume, which is where we get this 0.11 in terms of the mass. And that's also attributed to the fact that Mars is less dense than Earth. And indeed, we can see that here. There's Earth, the densest planet in the solar system. Venus, less dense, and then Mars, significantly less dense. And again, there's not as much heavy elements in the core of Mars. Surface gravity is quite comparable between Earth and Venus. They have, so you'd be a little bit lighter on Venus because the acceleration is a little bit less. Now, the acceleration on Mars, due to its less mass and less size, is significantly less. You'd only weigh 38% what you'd weigh on Earth. So you'd weigh less than half as much as on Earth. Now, this isn't as dramatic as your weight on the Moon, for example, where it's 1/6 or 0.15, but it's closer to how heavy you'd be on the Moon than how heavy you'd be on Earth. So you'd certainly be noticeably lighter if you were to walk around on the surface of Mars, which hopefully someday humans will walk around on the surface of Mars. In terms of escape velocity, it's much what you expect, because bigger planets have bigger gravitational pull, thus they take a greater velocity to escape. So we can see that Venus, being so Earth-like in terms of its size, has a just somewhat less escape velocity, again, what we'd expect, being a little bit less massive, and Mars has a significantly smaller escape velocity. Now, this is still significant, though. So this means landing on Mars is a big deal, because you accelerate very quickly as you approach the surface, because that's the other side of escape velocity. It's a very fast approach. And it also means that it's very difficult to plan a return mission from Mars. It takes a huge amount of energy to launch a rocket back off of Mars. Thus, we've never sent a mission, a scientific mission or otherwise, to the surface of Mars and then brought it back. There's never been any sample return from Mars because of this significant escape velocity. That's in stark contrast to the times we've gone to the Moon, where we've landed on the Moon and come back, both manned and unmanned more recently. In terms of the rotation period, This is the length of a day. All right, so you can think of this essentially as a day. And this is where things get quite interesting because we have the length of a day on Earth is 23.9 hours, okay? That's going to be our solar day. Now, the rotation period for Venus, let's see, actually, these are the sidereal days, excuse me. So this is the sidereal day at 23.9 hours. That makes sense because the solar day is slightly longer than the sidereal day. Let me go ahead and write that in because we talk a lot about the difference. So this row right here is sidereal day. So Earth has a sidereal day of 23.9 hours. Look at Venus, 243 Earth days. Its sidereal day is incredibly long. Venus rotates very, very slowly. And Venus rotates in a clockwise manner. Now, clockwise, you might think, oh, well, that's normal. But in the solar system, as viewed from above the ecliptic plane defined by basically the orbits of all the planets, everything rotates counterclockwise, both in orbit and axial rotation, except for Venus and one of the moons of one of the distant gas giants, which we can talk about later. But that's very unusual that Venus rotates clockwise. We call this in astronomy speak a retrograde orbit because it's going backwards, or the backwards rotation of any other planet. Now, this strange orbit was probably due to a series of large impacts. That's the best explanation for lots of strange behavior in the solar system, but it is very, very strange. The planet is nearly not rotating at all. You can see it's spinning so slowly around its own axis, and it's doing it in a way that's backwards. Now, going back to Mars, things are much more typical, or at least more comparable to Earth. The day length in hours is almost the same as on Earth. So the time it takes Mars to rotate around its own axis for the sun to rise and set is about the same on Mars. And that's nice in terms of what it would maybe perhaps colonizing Mars, because it'd be easy to say grow crops, assuming you have a good enough greenhouse to grow those crops in. Okay, and we'll talk more about the atmosphere of Mars and why you would need a greenhouse. Now, in terms of the surface area, again, Venus is smaller and Mars is much smaller. And that's just, again, proportional to diameter. And lastly, atmospheric pressure. This is something we will talk about a bit more. Now, atmospheric pressure on Earth is based on 1 atmosphere, so 1 ATM. By the way, 1 ATM is equivalent to 101,000 pascals, where a pascal is just a Newton, measurement of force, per meter. That's a pascal. Okay? That's the metric equivalent. Is 101,000 pascals. It's also equal to 760 millimeters of mercury, another typical way of measuring atmospheric pressure. But we can also say that's 1 ATM, 1 Earth pressure. Now check it out on Venus. It's 90 times greater. The pressure on Venus is incredible. That's a huge amount of pressure. 90 times greater. That's the equivalent pressure of diving to the deepest ocean trenches. That's a crushing amount of pressure. And that's just on the surface of the planet, not due to an ocean, but just due to the atmosphere. On the other hand, atmospheric pressure on Mars is tiny. There's almost no atmosphere. Now, it's not going to be the almost no atmosphere extreme that we saw from Mercury and the Moon. There is some atmosphere, but it's certainly, as you can see, dramatically, but 7 thousandths as strong in terms of pressure as Earth's atmosphere. Okay, so very low density atmosphere. So it's a good summary, a lot of information, obviously up front, we'll talk more about it, but this really summarizes some very interesting facts about the 3 quote-unquote Earth-like planets. And also, I think, clarifies what we mean by Earth-like, because really when we say Earth-like, we're really either referring to the size in the case of Venus or the day length in the case of Mars. There's some significant similarity. Here is a picture of Venus photographed by the Pioneer orbiter, so a spacecraft that flew from Earth and then adjusted its trajectory to be in orbit around Venus. And we can see Venus is completely covered in clouds. And this is important because this means that the day length of Venus had to be discovered completely by the spreading of a radar signal. There is no way to, just based on surface features, observe how fast Venus rotates because there's no surface features to track. Venus is completely shrouded in clouds. There's never any gap in the clouds of Venus. But if we bounce radar off the side, we can see in terms of its orbit, now it would be orbiting in the direction that we wouldn't expect, so clockwise. So we would have a blue shift on this side over here where the planet's moving away from us, and a red shift moving over here. We can appreciate for how difficult this would be for scientists because when they look at Venus, they would have a very hard time reading such a small amount of shifting in terms of the red shift and blue shift because the planet is moving in such a sluggish manner. But regardless, at some point in the mid-20th century, we were able to determine the incredibly slow rotational rate of Venus. We had known the rotational rate of Mars for a long time, which we'll talk about briefly. One, as evidence of how we are able to easily to determine the rotation rate of Mars, here is the quality of photographs that we took, back in 1988, so fairly recently. But you can see very clear surface features. You can see darker regions on the surface. You can clearly see the polar caps. So really, we can have a good view of the surface of Mars from Earth-based telescopes. And indeed, even back in the 1800s, so say the 1890s, we were able to get good enough surface photos of Mars through telescopes to observe dark patches that were misidentified by many people, including Percival Lowell, who thought that they were large reservoirs of water connected by canals. And this was under the premise that there was aliens, Martians, living on Mars, and we were seeing their activity. They had colonized the planet or spread across the entire planet in some sort of giant structure. Of course, that's not the case. There's no known life on Mars, certainly not an intelligent species that's building canals and large reservoirs. But this was just based on his observations of these dark patches that appeared to be unnatural based on the quality of the images, which were, of course, less high quality than these ones taken in 1988 because they were taken over 100 years earlier. But still, there was distinct features, and Percival would have known, among others, what the rotational rate of Mars was around its own axis. Okay? But he was wrong about Martians. Here's a picture of Percival. Your textbook makes a big deal about him in terms of a historical figure because he really did make Mars popular in the popular understanding of the planet. It gained a certain cultural significance because it was talked about and his publications were so widely known. And that fascination about Mars has persisted even today, over 130 years later, after Percival began observing Mars. We still look up at Mars and are so fascinated by it, and it's a place we want to know more about. So going back to Venus, because we're going to break down a few details of Venus before we return to Mars in a little bit more detail, let's take a look at this image, a composite image of Mars taken with a basically not visible light, but taken with some other type of wavelength. So probably a radar image. The resolution is about 3 kilometers. So we can certainly, based on that resolution, we can certainly say that this is a radar image. It's been artificially colored. There's no such thing as blue radar and green radar, but they would just match them up within the visible spectrum. So in other words, blue would correspond to shorter wavelengths, so that's less bumpy regions or deeper regions, and then we can think of the mountains, as being red and higher up. When we look at Mars, we can see lots of features underneath those clouds. There are indeed mountains and valleys and lots of activity, but again, all completely shrouded, which is why we need to use radar imaging. There's no way to take a visual image through the clouds of Mars. They're opaque to visible light, to the visible spectrum. Now, returning to the day and year of Mars, I'll upfront say the most interesting thing about it, and that it's that the solar day of, I said Mars, I'm going to say Venus, excuse me, but the solar day of Venus is approximately 1/2 the sidereal day. Now, if you think I'm writing a typo here, you'd certainly be forgiven for thinking that, because I make those mistakes from time to time, and you might think, well, no, sidereal days are always going to be longer than solar days. It can't be the other way around. You can't have a solar day that's shorter, right? Solar days have to be longer than sidereal days. Think about Earth, right? Think even about the strange case we talked about in chapter 9 of Mercury. Mercury has a very odd orbit where its day is 2/3 as long as its year, but even then we have certainly that the solar day is much longer than the sidereal day. Okay, and on Earth, it's all, they're pretty close, but again, our solar day is about 4 minutes longer than the sidereal day. But here I'm saying for Venus, the solar day is shorter than the sidereal day, and by a factor of 2, it's only half as long. How could that be possible? Well, the reason that's possible is because the sidereal day, and that's the time it takes Venus to rotate around its own axis relative to some fixed background, often thought of as distant stars. So the sidereal day of Venus is approximately equal to its year. Okay, so it basically takes, and that's kind of like the moon in terms of its orbit, right? The rotation of the moon around its axis is about the same as its orbital period around Earth. But what's different is the moon's orbiting Earth, not orbiting the sun, so it doesn't affect the rising and the setting of the sun relative to the moon in the same way that this relationship affects the rising and setting of the sun relative to Venus. And let's visualize that. So let's start here, the start of the day and year. okay? At this point, start right there. And let's carry on with what things are going to look like. So this is going to be our point that we're interested in, pointing initially towards the sun. And notice that it takes a full year for that point to come back around. So we can see that at the end of year, it would look identical. We'd be back exactly facing the sun at the same point in the orbit, okay? Because they're about the same. A sidereal day is a year, okay? But then let's track this point. So as we go, we see that the sun sets about here. Then we're at midnight, and then we're at sunrise. Wow, that was fast. And all of a sudden, we're facing the sun again, all right? So the end of solar day 1 occurs at only half an orbit. But of course, that makes sense because that's half a sidereal day. The planet has completed 1/2 a rotation. Look, initially we're pointing this way. After half a rotation, we're pointing towards the right. We're pointing towards the left. Now we're pointing to the right. Half rotation. But a half rotation for a planet that has a sidereal day approximately equal to its year means that we finished a solar day because we're back to facing the sun. That's how we get the relationship. So in fact, when a sidereal day is equal to a year for an orbiting planet, such as Venus, then we have a solar day that's half as long as a sidereal day. And we can continue on, as the figure does. We can then get another sunset, basically get a midnight, get a point where we're going to come back around, and then we can have the end of rotation right about there. And the reason that the end of rotation doesn't exactly match up is because it's not a perfect relationship, but it's pretty close. All right. So in other words, the sidereal day is approximately a year, and the solar day of Venus is approximately 1/2 a sidereal day. Amazing stuff. Maybe not as complicated as the orbit of Mercury, which is nice, I suppose, but also equally fascinating to have such a dramatic difference between solar day and sidereal day. Well, getting back down to the surface of Venus, what we know about it from radar images, we see that there are impact craters. So Venus does have a significant number of craters, all right, more than Earth, certainly, because there's no, kind of plants and erosion and water cycle to wash them away, but not as many as other planets. There has been significant amounts of volcanic activity covering up those craters. And a lot of craters break up in that very thick atmosphere of Venus. So we have craters that are many pieces, which are more common on Venus than other worlds. And there's also lots of volcanic activity, right? The volcanic activity means that there's not that many craters because the planet is so hot, a temperature that we'll quantify in just a few moments. The planet is so hot that the surface there's just molten rock and molten metal just from the ambient temperature. It's, the surface is just melted or half melted. So lava can very easily bubble up. There's not a lot of solid, solidified rock and metal to stop it. So there's these big volcanic pancake-shaped domes that form where lava just kind of bubbles up and pushes the ground out of the way. There's more traditional volcanoes as well, but there's just a huge amount and a huge variety of volcanic activity on the surface of Venus. Here's an example where there's an impact crater that then is surrounded by tectonic cracking. So one thing that we do see on Venus are tectonics. And I want to be clear on this word because we're going to say that we see tectonics on Mars as well. Both Venus and Mars have tectonics, but tectonics are not the same as tectonic plates. Tectonics just means that we have some sort of surface activity that's driven from energy and heat within the planet, basically cracking the surface, as we can see here, creating cracks and, big splits and so on, kind of like a cooling pie that's going to split and crack as it cools. That's tectonics. And, in this case, things are heated and then cooled over and over again. It's a continual process. So that's just heat from within, being visible on the surface of the planet. Tectonic plates are unique to Earth, where we have these freely moving plates that are shifting relative to each other and rearranging over hundreds of millions of years. We don't see any evidence of that on Venus, nor do we see it on Mars. All right, but here we have cratering surrounded by tectonics. Here we have other examples of tectonics with lots of ridges and cracks. So a very dramatic example of lots of heat coming up from the inside of the planet. And here we actually see a lander. We have landed on the surface of the planet. In this case, we have the Venera 13, a Russian spacecraft that landed successfully on the surface of Venus. It didn't last very long because it's such a harsh environment with that incredible density and incredible temperature, again, which we'll quantify in just a moment. But we were able to, the scientific community in general and the Russians specifically, were able to get these images of the surface of the planet showing that, there's rocky surface, showing the horizon in terms of its kind of gray composition, and, the horizon over here. And just showing that indeed this is what the surface of the planet looks like. We've never sent any rovers to Mars. We haven't engineered anything that would, never sent any rovers to Venus. We haven't engineered anything that would survive, but perhaps someday we will be able to have longer term surface missions on Venus. But for now, we just have fleeting images that have been taken a few times. And this was way back in the 1970s. We haven't returned that much because there's not a lot of active research with the surface of Venus in terms of rock samples or anything like that, unlike what's going on currently with Mars. Now, again, very, very harsh environment on Venus. And in fact, if we look at the layers of the atmosphere, starting at the upper atmosphere, the mesosphere, and then the stratosphere, and then some sort of cloud layer that probably includes lots of sulfur as well as H2SO4, ammonia. And then we go down, then we basically have a troposphere, so a lower atmosphere that is almost entirely CO2, and big volcanoes. But look at the temperature. As we drop down, we have some lower temperatures in the upper atmosphere, but after we drop down underneath the sulfur clouds into that CO2 troposphere, the surface temperature shoots all the way up to 700 Kelvin. All right. So if we subtract 273, we could convert this over to Celsius. So that's going to give us about 450 degrees Celsius. Incredibly hot enough to, as I said, to melt metals and rocks. The surface temperature is unbelievable. What makes it so hot at the surface of Venus? Well, that incredibly dense atmosphere certainly has something to do with it, but also this huge amount of CO2. There is a runaway greenhouse effect. So a runaway greenhouse effect. There's so much CO2 in the atmosphere that the heat is just trapped. Whatever heat radiates away from the surface gets up into the CO2-rich atmosphere and just gets reflected back down to the surface. So it's just a closed environment, just staying at this incredibly high temperature with just a slow amount of heat as much as can seeping through the clouds, but then that maintains an equilibrium that has a very, very high temperature. All right. Obviously, completely hostile to life. No life could live at such high temperatures. Okay, so that wraps up Venus. Big takeaways: incredibly hot planet with a greenhouse effect, very unusual day. Otherwise, very, very similar in size and volume and mass and gravitational attraction to Earth. Okay, so interesting planet, right? Well, so is Mars. And let's talk a bit about Mars. Here we have an image, much higher resolution than that surface-based one taken in 1988. Here we have one taken by and obtained in June 2001 when Mars was only 68 million kilometers away. All right, so incredible resolution taken by the Hubble space-based telescope, so instead of ground-based. All right, here are images actually taken on the surface of Mars from the Mars Pathfinder mission. So one of those rovers that I mentioned, one of the smallest first ones. We have many generations of rovers since then, and tons of active research going on. If we look, we can see that Mars is covered in a significant amount of craters, also lots of valleys and landslides, lots of sandy features like the sand dunes that exist inside these craters. So like a sandy reddish dust covers the surface of Mars. It appears to blow around regularly because we couldn't get this structure of sand dunes if there isn't some sort of wind. We'll talk more about the wind on Mars in a moment. Now, the thing is, since we've never had a return mission from Mars, because it is rather difficult, the only Martian rocks we have are actual Martian meteorites. So these are rocks that would have been flung up into space during a particularly large impact, and then eventually got pulled into Earth's gravity and then fell on down to Earth as a meteorite. Now, to identify that this rock originally came from Mars is based on chemical composition of other rocks that have been analyzed on Mars by Mars-based rovers and based space probes. Okay, So here we're looking at a high quality laser ranging image of the surface. This is basically showing the different elevations of the surface of Mars. We can see that Mars basically has one continent. Now, again, I don't want you to be confused with plate tectonics. There's no evidence of active plate tectonics on Mars, not at all. But there's basically one large continent that has mountains and valleys and so on. And then there's a large flat region that's more like an ocean basin. And that's kind of the planet is one continent that takes up over half the planet, and then a lower large flat valley that takes up less than half. All right, and then another valley region over here. And these are just the two sides of the planet that we're looking at. Mars is rather famous for its Olympus Mons, which is the largest known volcano in the solar system. So bigger than anything we see on Earth, bigger than anything we see on Venus, even bigger than anything we see on very active volcanic moons like Io, which is the moon of Jupiter. It's just a dramatic, huge volcano. It's a very large shield volcano, which means that it's not steep. It's very spread out, but it still has an incredible elevation. Here is a region of Mars known as the Valles Marineris, and this region is famous for its evidence of tectonics. Okay, so tectonics. Because what we're seeing here is a place where the surface of Mars was broken apart due to internal energy coming up from Mars. It would have been formed billions of years ago, but basically this was a splitting of the surface of Mars, a pulling apart, and a leaving of a huge rift in the surface. Kind of like the rifts that we see in rift valleys like in Africa where plates are pulling apart, but instead don't think of it as freely moving tectonic plates moving apart on Mars, but think of the whole surface just with one big crack forming. All right, so there's just this dramatic crack. Indeed, we can see it here as well to show the sheer scale of it, with how much of the planet it takes up. It's much bigger than the Grand Canyon, right? So Mars certainly has large features, biggest mountain, not quite the biggest valley in the solar system, but something that puts the Grand Canyon to shame. All right, here we can see examples of landslides. There's lots of examples of landslides. And notice just the high quality images, right? We know so much more about Mars because we're able to take these visible images of Mars. We're not obscured by the cloud layer. All right, so it's not as hostile an environment. So these are the landslides where a huge cliff was left to just slide away. Here are some landing locations of Viking 1, Pathfinder, and Viking 2. All right, here we see evidence of water. Now, not liquid water, not flowing water, but there's evidence of water frost. All right, this is taken by Viking 2. We see frost forming on the rocks. We also see examples of lots of movement of surfaces, and that's due to this idea of dust devils, which are kind of like small scale tornadoes, because Mars is driven by large dust storms, and not just wind that's depositing dust, but actual swirling dust storms that lift up dust and just remove it from certain regions, which is very important in terms of the actual transport of minerals across the surface, and has been very helpful for Mars-based exploration for scientists because it helps uncover the solar panels on space probes. Because when a really strong wind comes, it sort of will brush everything off of the rover and its solar panels and leave it able then to pick up more energy. Whereas if there was just a steady wind depositing more and more dust, everything would just get covered with dust over time. Here we see examples of wind erosion on the surface of Mars, right? And this low quality image. Here we're actually looking at one of the polar caps. So the polar caps of Mars do have frozen water ice. Okay, so water ice does seem to be not exactly everywhere on Mars by any means, but does exist in small pockets at the poles and near the poles, such as where you can see Viking 2 landed near the pole, and it was able to observe some water ice. All right. We also have a case where the Phoenix lander landed basically right on the probe, right on the pole, dug down into the Martian soil, and then was able to notice that there was some ice that formed, and then the ice sublimated over the next few days, and scientists were able to base that off of the rate of sublimation and the known density of of Mars's atmosphere, that what the ice that formed had to be water ice, so actual H2O ice, not nitrogen ice, for example, but actual water ice. So there definitely is water ice on Mars. All right. Now there's also examples of past flowing liquid water. We see channels that dramatically look like deltas that we see on the surface of Earth. We see like what looks like dried riverbeds. We see examples of big alluvial gullies and so on. We see, other examples of water features. We even see rocks that we associate with water features in terms of sedimentary rocks, really clear sedimentation. So there's just a lot of evidence, a huge body of evidence suggesting that Mars must have had liquid flowing water, lakes, perhaps oceans, rivers flowing, waterfalls of liquid water at some point in its history. But it's been billions of years since that happened. So we're looking at these dried riverbeds on Mars that haven't been dry for thousands of years, not even millions of years, but have been dry for billions of years. Well, why is that? Well, unlike Venus, Mars experienced a runaway refrigerator effect. So what happened is early in Mars's history, it had liquid water. So did Venus. But what happened is instead of the planet holding on to that liquid water, its smaller size and lack of a strong magnetic field meant that over time, just more and more of those water molecules escaped into space. All right, and especially the hydrogen escaped into space. And without the hydrogen, the oxygen didn't have any hydrogen to bond to make H2O. And so we were left with a very thin atmosphere that just got thinner and thinner over time, and then no longer could support a hydrocycle. Couldn't support, say, rain clouds and flowing water and the necessary features to maintain water on the surface. And then eventually the planet got so cold that any water that was left over just froze and probably froze down into the rock and sort of seeped away. And we were left with these dry riverbeds and dry river features that we see on the surface of Mars. So there's a runaway refrigerator effect that can be explained probably by Mars's small size and, again, lack of magnetic field. Interestingly, Venus also lacks a strong magnetic field, which is probably due to its very slow rotation, as that's one of the features that a planet needs for a magnetic field is a rather fast rotation as well as a molten core. Mars likely lacks a molten core, although it does have sufficient rotation because we know its day length is similar to Earth's. Regardless, we have a atmosphere now, planetary conditions that are just not right for liquid water. There's no way that liquid water could exist in the scale that we see evidence of it now and couldn't have, again, for billions of years. So it's probably basically for the first about 1 billion year of Mars's history, perhaps a little bit less on the scale of 800 million years, that there would have been liquid water. And in the last 3 billion years, or 2.5 billion, there's been none. Okay? Now, what is interesting is the atmosphere that's left that does create some scattering, in terms of, actually, showing a little bit of blue, though the sky is more often red in color than Earth's blue sky. But the atmosphere, that very, very low density atmosphere that Mars has, is actually also CO2, just like Venus. But it's not enough to create any significant amount of greenhouse effect. In fact, the CO2 that's on Mars is all the better because it keeps Mars from being too cold. It's already a very cold planet, but it keeps it from being completely hostile in terms of being cold, because there is a little bit of CO2 in the atmosphere, or that the very small atmosphere is almost entirely CO2. And so then it does retain some greenhouse effect. But again, you saw how low the density was back on the previous table, so it's just a tiny amount of CO2. But it is important to acknowledge that both Venus and Mars, so Venus and Mars, both have atmospheres that are almost entirely CO2, but for very different reasons, okay? And with very different consequences, one with a runaway greenhouse effect and one with a runaway refrigerator effect. But neither of them has significant amounts of free oxygen nor nitrogen, unlike Earth's atmosphere. Right? So fascinating in terms of the chemical composition. And we're going to finish off with debunking the face on Mars. Perhaps you've seen this image showing, clear evidence that there's some Martians, building giant, almost pyramid-like structures showing human-like faces. Well, this is just an effect of shadowing and a low-resolution image. If we take that same take an image of that same mountain or volcanic feature at 20 times better resolution, we can clearly see the shadows that made it look like there was eyes, but there's not. There's just cracking and so on. So don't jump to conclusions just based off of one image. And that concludes our lecture introducing Venus and Mars. Thank you so much for watching. I hope it has been interesting and informative.